This segment covers arbitration, the coordination of uncoordinated signals into coordinated signals. I think I'm missing something. Oh yes, I've added a library called underbar unity for which every function the delay is 1 picosecond. On the normal library the delays are 30, 40, and 50 picoseconds. And I will demonstrate that library. I feel like I'm missing something else. Oh well, the details. Arbitration begins with a mutex, which is a mutual exclusion element. It's a pair of cross-coupled NANDs with a filter across the two outputs. And the filter ensures that G1 or G2 is high, but never both at the same time. Now the way this works is that the R's are requests and the G's are the grants. And the R's can arrive at any time, even simultaneously. If they arrive simultaneously, the filter will determine to grant either G1 or G2, but not both. Say G1 is granted, and the grant will go back to the logic that generated R1. Pretty soon they're done with the grant and R1 goes low. As soon as R1 goes low, G1 will go low and G2 will be granted. And then G2 goes back, they do their grant, and then R2 is released, and G2 goes low. If R1 came along at the same time, then G1 is granted. The point is that there's G1 and G2 are mutually exclusive. R1 and R2 are not. They can arrive simultaneously in any order. They're not coordinated. G1 and G2 are coordinated into mutual exclusivity. Note, G1 and G2 were mislabeled on the original slide set and are corrected on the new slide set. The arbiter puts a bit of logic around the mutex that allows the grants to hold off each other until the grants actually go low. It also has an output R and an input G, and these, the R can itself be arbitrated. So we can gang these together as we do down here. The R of one arbiter goes into R1 of an arbiter, and the R of the other arbiter goes into R2. So this arbiter is arbitrating these two arbiters. So we're arbitrating the arbitrations. Now the root arbiter ties R and G together. So now we can arbitrate 4 signals. If we're only arbitrating 2 signals, we just tie the R and G together of the individual arbiter and we arbitrate 2 signals. So we can arbitrate as many signals as we want with as large a tree of arbiters as we want to build. The downside of this is that the requests go all the way through the tree, through R and G, and back up through the tree to get the grant. So the bigger this tree gets, the slower the arbitration gets. This is the textbook arbiter. And now we're going to turn the textbook arbiter into an NCL arbiter. So this is the NCL versions of the textbook arbiter. And you know, these are the C elements are 2 of 2 and the OR is a 1 of. And the AND gate, we can do a De Morgan and make it a 1 of, or we can do it this way. I'm not sure which is most efficient, so I've shown both of them. Now, if we look at the behavior of R1 and G1 and R2 and G2, we see that R1 goes high, and then G1 goes high, after which R1 goes low, and then G1 goes low, after which R1 can go high again. So what's going on here is that these signals are behaving exactly as the monotonic transitioning of an oscillation. So we're going to take the arbiter and turn it into a flow component that arbitrates 2 independently flowing rails, R0 and R1, into a single dual rail output flow. This is the output dual rail half oscillation, and you'll notice that we've closed it here. We're auto-consuming it because all we want to do is show the signals on the waveform viewer here. This is the flow specification for the dual rail arbiter, and this is the Verilog code in the test bench and the make file and so forth. This is ARB-D, the dual rail arbiter simulation program. Free to dual is the arbiter itself, and we drive the arbiter with 2 bit streams from the B input of the test bench, bit 6 and bit 5. And we drive the arbiter only with zero values of each bit. If the value of the bit is 1, we immediately close with it and essentially sync the bit. So what this does is makes the input to the arbiter a little more random than it would be if we used all the bits. Also, we're auto-consuming the output because we only want to look at the signals on the waveform viewer. These are the waveforms of ARB-D, the simulation of the dual rail arbiter. Down here you can see the input to the arbiter, R0 and R1. And you can see that the signals are not coordinated in any sense whatever. Here you can see the output of the arbiter, and you can see that it's a well-behaved dual rail output. The data states never overlap, and there's always a null state between each data state. Up here you can see the input from the test bench, and you can see the ones being skipped. The short pulses are the ones being skipped, and the long pulses are the zeros waiting to be arbitrated. Over here you can see that there's a bunch of ones being skipped on bit 5, and while these ones are being skipped, bit 6 gets in 3 grants, right? So you can see there's 3 grants here while we're waiting for the ones to be skipped on 5. The next example is the arbitration of 3 independent flowing rails into a single trinary variable flow. The first thing we do is arbitrate R0 and R1 into a dual rail flow, and then we arbitrate the completeness of the dual rail and R2 into a flow which is an enable of the dual rail or the output of R2 into the trinary 2 rail. This is the flow specification, and this is the simulation program. This is the waveforms from the trinary arbiter. These are the inputs, R0 to R2. You can see that they're completely uncoordinated being presented to the arbiter. This is the trinary output. You can see that it's a well-behaving and well-formed trinary variable. And these are the inputs from the test bench. These are all the ones being skipped and so forth. In this case, we're using bits 0, 1, and 2 out of the test bench. The next example is arbitrating 4 independently flowing rails into a single quad rail variable flow. We do this by arbitrating 2 at a time into dual rail. So we arbitrate R0 and R1 into a dual rail, R2 and R3 into a dual rail, and then we arbitrate the completeness of the dual rails to see which one of those is going to flow into the quad rail. So this is the specification code for the simulation for the arbiter, and this is ARBQ is the simulation program. These are the waveforms for the quaternary arbitration. These are R0 to R3 is the input to the arbiter. You can see that they're not in any sense coordinated. This is the output of the arbiter, the quaternary variable, and you can see that it's a well-formed quaternary variable behaving properly. These are the inputs from the test bench. Now we're using bits 0, 1, 2, and 3. These are the skipping the ones and so forth. The next example arbitrates 2 dual rail flows into a single output dual rail flow. So we create the 2 dual rail flows from uncoordinated inputs to begin with, but at this point we have 2 dual rail flows. And we take the completenesses of the 2 dual rails, arbitrate them, and generate enables for the 2 dual rail flows into the single dual rail output flow. This is the flow specification for the arbiter, and ARB-DD, ARB-dual-dual, is the program that simulates the dual rail to dual rail arbitration. These are the waveforms for the dual rail to dual rail arbitration simulation. Down here we have 1 dual rail input. You can see that it's a well-formed dual rail signal. Here we have the other dual rail input. You can see that it's a well-formed dual rail signal, but you can also see that the 2 are uncoordinated. They're quite out of phase. Here is the output dual rail signal. You can see that it's a well-formed dual rail signal. And these are the inputs from the test bench and skipping zeros and so forth. Now, the output dual rail signal has fallen into a bit of a pattern here. and it's fairly stable for a long time, but we can see that later on it starts changing, right? So here we have 3, 1, 3, 1, and it starts being quite different towards the end. In the beginning, we indicated that we were going to demonstrate the unity library, a library in which all the gate delays are 1 picosecond, in contrast to the standard library in which all the gate delays are 30, 40, or 50 picoseconds, depending on the input of the gate. And we're going to demonstrate the unity library in relation to the dual-to-dual arbitration that we just looked at. Okay, so this is the dual-to-dual arbitration, and this is done with a standard library. And if we shrink this down, we can to 100 nanoseconds here scale. We can see that it took about 87 nanoseconds to complete the test bench. So now this is the test bench run with the Unity library. We're still at the same 100 nanosecond scale, and you can see that it takes about 15 nanoseconds to run the test bench. Now the question is, did the test bench run correctly? So if we expand this out, we can see that all the signals are there. Right, this is the dual rail input. It's a well-formed dual rail signal. This is the other dual rail input. It's a well-formed dual rail signal. And this is the dual rail output. And it's a well-formed dual rail signal. You can see that the timings are a little bit different. We have a short data wavefront here and a long data wavefront and so forth. But they're similar. We have 2, 2, 2, 2, just like the standard library did. And if we go to the end of this, we can see that it changes in a similar way to the standard library. So we start getting 3, 1, 3, 1, and so forth. And then 1, 1, and 1, 1 as the test bench runs out. So using the Unity library, it gives you a first-order confidence that your NCL circuit is actually delay insensitive if it runs correctly with such a range of delays in the library.